In this video, we will be finding the maximum likelihood estimator for the Rayleigh distribution. For more on this topic, you need to subscribe to this channel. This distribution is not so popular in statistical inference. Solution. The first thing to do for the moment likelihood estimation is to take the likelihood function. The likelihood function of the distribution given, in this case, is the Rayleigh distribution, is the product sum which ranges from I to n x all over sigma squared exponential negative x squared all over 2 sigma squared. So we are taking the product sum. This product sum means the likelihood is equal to 1 all over sigma squared 1 x I, that is x1 exponential x1 exponential x1 squared all over 2 sigma squared multiplied by 1 all over sigma squared 2 x2 exponential x2 squared all over 2 sigma squared multiplied by, that's how it continues, 1 all over sigma squared x, this time n, xi exponential negative x squared I all over 2 sigma squared. So this is what we'll get. It then means that our likelihood function can be written as 1 all over sigma squared raised to the power of n. If we sum this one, if we sum it, you will get summation of xi's exponential negative. If we sum these xi's, we'll get summation of xi squared all over 2 sigma squared. So this is what we'll get. The next thing to do for the maximum likelihood estimation is to take the log. But in this case, before we take the log, we'll have to arrange this first. So arranging this, we have our likelihood function to be equal to, we can write it as sigma negative 2n multiplied by summation of xi exponential summation of xi squared all over 2 sigma squared. So this is what we get. The next thing to do is to take the log. The purpose of writing it this way is for we to take the log easily. So taking the log, we get log f of x sigma to be equal to, if we take the log of this, we get negative 2n log sigma plus summation of log xi. If you take the log of an exponential distribution, you get that same thing. So we have negative summation of xi squared all over 2 sigma squared. So this is what we get. The next thing to do is for we to take the differentiation, the differential, or take the derivative. If we take the derivative, that means the derivative of log L. If you take the derivative with respect to sigma squared, we'll get this as, the whole of this will give us negative 2n all over sigma plus, if you take the log of the differential or derivative of this, we'll get 0. This is because there is nothing like sigma squared here. Now, the next thing to do is to take the differential of this. For we to take the derivative of this, we use what is called the quotient rule of differentiation, which states that it then means our dy all over the sigma squared will be equal to v du all over the sigma squared minus u dv all over the sigma squared all over v squared. That means this. So we are taking this as our u and this as our v. So it then means that this is equal to v. We bring down v, which is 2 sigma squared, the u all over the sigma. That means the u, the whole of this, all over the sigma. If we differentiate it, we get 0. Minus u. We take our u. Our u is summation of xi squared. Then we differentiate the v all over the sigma square. The v all over the sigma square, we get, if this comes here, we get 4 sigma. We get 4 sigma in bracket, because these two will go over this place and 2 minus 1. Then all over b squared, which is this. We have 2 sigma squared all squared. So it then means that our dy, the sigma squared, will be equal to negative 4 sigma summation of x I squared all over 4 sigma 4. So that is what we put here. So we have here as negative 4 sigma summation of xi squared all over 4 sigma 4. So this is what we get. So to get the maximum is for we to equate the whole of this to 0 to get the maximum. But before we do that, we can cancel this. This can cancel this. Likewise, the sigma can cancel this to give us 3 here. So the next thing to write is the whole of this will now be, the whole of this, the whole of our derivative will now be negative 2n all over sigma plus summation of xi squared all over sigma 3. So we'll now equate this to 0. This is what we get. So equating to 0, we get, let's come over to this side. Let's come over to this side. So for more on this topic, you need to subscribe to this channel. We should remember that we are still looking for the real distribution, the MLE of the real distribution. So if we equate that to 0, we get negative 2n all over sigma plus summation of xi squared all over sigma 3 is equal to 0. Of course, this can go over to this place, which will give us negative 2n all over sigma to be equal to negative summation xi squared all over sigma 3. So this will cancel this. We can now bring this here to give us sigma 3 all over sigma to be equal to summation of xi squared all over 2n. So this will cancel this to give us square. So sigma squared will be equal to summation of xi squared all over 2n. Remember, this is ranging from 1 to n. So we have, if we take the square of both sides, we'll now get our sigma estimate to be equal to the square root of 1 all over 2n summation of xi, I ranging from 1 to n, all squared. So this is now the maximum likelihood estimation for the real distribution. For more on this topic, you need to subscribe to this channel. It is very simple to compute the real distribution. So if we follow the procedure, first, we'll take the likelihood function. Second, we take the logarithm of that function. And third, we take the derivative. We'll arrive at this for the real distribution. For more of this, you need to subscribe to this channel.